Hi, everyone, and welcome to online lecture 10, part 2. So in part 1, we talked about some of the theoretical underpinnings of a simple linear regression. And in this part, we're going to talk about how you actually complete one and write one up according to Laird. Okay. So we're actually going to stick with the same example that we did for correlation, which is the time spent watching TV and cholesterol concentration. Okay, so in this case, however, we're going to look at time spent watching TV as our independent variable, and we are looking to predict our dependent variable of cholesterol concentration. So you can see that right here, we have time TV as our independent variable, cholesterol is our dependent variable, and then of course there's an ID number associated with each one that we don't really care about. Okay, and here's our data view. Okay. Now, I know I had said I was going to skip page 7 in the lecture from last time. I said 6 and then 8 to 20, but I actually do want to look at this real quick. So the first two assumptions of linear regression relate to the study design, as we had talked about. You have a continuous dependent variable and you have a continuous independent variable. Well, good. Time TV, cholesterol concentration, both fit that bill, so we are in good shape. However, there are several other assumptions with this test that have to be met. Okay, so the first one, there needs to be a linear relationship between dependent and independent variables. And we're going to use a scatter plot like we did before to assess that. And I know that's super fun because it's sometimes hard to tell, but we'll do the best we can. And you should have independence of observations, which you can easily check using the Durbin-Watson statistics. So that's good. And we'll talk that through. That one's pretty straightforward. There should be no significant outliers. Now we get a little bit of help this time. We do look at the scatter plot, but there's another thing we can look at as well to help us diagnose any outliers in this case. Your data needs to show homoscedasticity. Okay, so in other words, the variance of the errors or residuals needs to be constant across all values of the independent variable. And we'll look at that a little bit more, okay? And then we need to check the residual or errors of the regression line to make sure that they are approximately normally distributed. So that's what we're going to do. All right, that's our approach. So we start off by establishing if a linear relationship exists. And you've seen this before. We've seen the actual linear one, the nonlinear one, and the other nonlinear one that's also non-monotonic. So I think you probably recall how to create a scatter plot in SPSS statistics, but in case you don't, let's go through it. So you go into graphs, you go into chart builder. You'll get this. We're going to choose scatter dot from down here, like so. And then we're going to bring that into this main area. We're going to drag this first one into the main area. So we drag it in there. Okay. Then you'll be presented with the screen below, which shows a simple scatter plot. And then we're going to drag over time. This time it does matter which we drag to which, okay? So time TV is our independent variable. It goes by the x-axis. Cholesterol is our dependent variable and goes to the y-axis. So independent variable to x on the bottom, dependent to y along the side. Okay. And as you can see, that's what they've done right here. All right. And once again, they are telling you to remember that what you see in that little preview area is not necessarily reflective of what you'll see when you actually run the graph. Okay, so don't pay much attention to that. And then finally, under element properties, you're going to choose y-axis, as they do here. And you're going to click off the minimum and set it to 0 so that you're at least starting your y-axis at 0. Okay, and that means you'll be able to see your intercept a little more clearly. Okay. Then we click apply and we click OK. And then we get this. Okay. Now, this one is relatively straightforward. It's not too bad. There does seem to be a linear relationship here, right? You can kind of see that straight line going through a little bit at an angle, not a great angle, but a little bit. Okay. Yeah. And it is telling you here to be careful of the scales you use. That sometimes can throw you off a little bit. But I think you can probably pretty much stick with what SPSS gives you and what this guide gives you. Okay. So linear relationship, no linear relationship. That's what we consider a blob on the right. In this case, it's not the best linear relationship, but we do have a linear relationship here. And so we can say that that was established. Now we might also note that we have this little outlier, or what looks like an outlier, happening over here. We're probably going to want to focus on that in a little while. So this tells you what you can do. If you have a linear relationship, you get to move on, of course. If you don't have a linear relationship, you might be able to transform or something like that. Now, for our homework, okay, and I mentioned this a little bit, but let me be very clear. For our homework, you are going to test for all the assumptions, but you're going to proceed regardless of what you get. So even if it's a nonlinear relationship, you don't have to go through the process of trying to transform, or I don't expect you to run a polynomial regression, and I don't expect you to run a nonlinear regression. So you're just going to continue on the path of linear regression, even if you do not meet this assumption. But I would like you to note whether or not you feel you met this assumption. Okay, so we're not going to look very much at those three things. Okay. So now let's move on to the procedure. Because in order to check the remaining assumptions of this test, you need to run the linear regression procedure. And as they mentioned here, it's because many of the assumptions rely on the residuals, which can only be calculated once we have the regression line. Okay, so let's run it. We go under Analyze, Regression, Linear. Analyze, Regression, Linear. Okay. By the way, I'll point out under regression, look at all these wonderful, beautiful things that can be done. We'll talk a little bit about a couple of them later on, but for now, we're just going to focus on linear. And you'll be presented with this linear regression dialog box. And we're going to start off by moving the dependent variable of cholesterol to dependent and the independent variable of time TV to time TV. Just like they did here. Okay, so next we're going to click off statistics. And I'll show you, we're going to check off quite a few things here. In addition to what's already checked for the estimates, And model fits already checked, yes. In addition to those two, we're actually just going to make sure we check off confidence intervals, Durbin-Watson, case-wise diagnostics with outliers outside 3 standard deviations. All right. Then we click continue. Then we're going to do so when we click continue, let me just show you what happens. We go back here to this main dialog box. So you click statistics, you clicked off all those different things, then you're back here. Next, you're going to click plots. Okay. So you click the plots button. This is what you're faced with. Now you're going to transfer the Z resid to Y and the Z predict to X, or Z pred to X. So what it's going to be plotting for you using that is basically your predicted outcomes, but Z-scores of them, and your residuals, but Z-scores of them. Okay. I wouldn't worry too much about exactly what it's giving you, and I'd worry more about just how you're going to interpret it. So then we select both histogram and normal probability plot. Then we click continue, and then we can click OK to get the output. Okay. Now we can actually start checking our observations. Checking our assumptions, excuse me. The first one being independence of observation. So in order to do this, remember we said we're going to use this Durbin-Watson statistic. Okay, this occurs with the model summary by the R and R square and adjusted R square. And here's our Durbin-Watson. Now they say that what you want is your Durbin-Watson to be really close to 2. As close to 2 as possible. So I know you would like some kind of cutoff. So why don't we say the following for the purposes of this course and for the purposes of saying whether or not you met this assumption. I would say if you're between 1.5 and 2.5, you're okay. So again, I would say that if you're between 1.5 and 2.5, you're okay. If you're outside of there, you've missed this assumption. You do not have independence of observations. Okay. Now, if you have independence of errors, you can move on to the next section, which is dealing with outliers. And if you don't, then what's going on is that there was actually a good description of this. Your errors are correlated and you have to do something different, like a time series analysis. There we go. Yeah. So for example, if you tested your participants over time, you might enter your participants in the order you tested them. And then we could look for correlation across time, which we might expect. Okay. All right. All right. So that's your Durbin-Watson. And like I said, basically you're just looking for independence of your residuals. Hopefully we get that, and then we can move on. Next, we have outliers. Now, we suspected that this would be an outlier when we saw it before. But now we have case-wise diagnostics, which will help us truly determine if we have an outlier. So what it's going to do is it's going to give you the case number, in this case 91, and it's going to tell you how many standard deviations you are away, or give you a standardized residual, which in this case is 4.059. Okay. So 4.059 is greater than 3 standard deviations away. If this had been negative 4.059, it would still be greater than 3 standard deviations away, right? It's greater than the cutoff of 3 standard deviations. Okay. All right. So we've got a problem with an outlier. Okay. So what would I like you to do if there's a problem with an outlier? Well, there's all kinds of choices to deal with outliers. In this specific case, you are going to move on. However, I would like you to run the analysis with and without the outlier, okay? Because we don't have a data entry error. We most likely don't have a measurement error. And so it's a genuinely unusual value. So it says you can keep the outlier, you can remove the outlier as a last resort. And one of the ideal ways to deal with this is to run it with and without the outlier. Now, if you have multiple outliers, you still would only do this procedure once, with all your outliers, without all your outliers, okay? Now, it does say that if you think you have more than one outlier, just take a look at remove the most extreme one and run your case-wise diagnostic again, because those may disappear. Those may no longer be outliers once you get rid of the really problematic one. And then you can put it back in, run it with, run it without. Okay. So I will say that if this comes up more than once on your homework in terms of outliers, only do it once. So we can talk about that a little more in class, but I don't want you to have to go through the process of running with and without an outlier more than once. So you can just run it the first time that it comes up. Okay. All right. All right. So that's outliers. Okay. So now we go to testing for heteroscedasticity. This is looking at the assumption that the variance of the errors is constant across the values of the independent variable. Okay. So here's what we're looking for in our scatter plot. We're looking for either an increasing funnel, a decreasing funnel, or a fan. Okay. Now, when I look up here, thankfully, I don't really see much of that. So I think we're okay. So if there's no heteroscedasticity, that's great. It means we have homoscedasticity. It's the same across our independent levels of our independent variable. Okay. And as you can see, it says right here, there was homoscedasticity as assessed by visual inspection of a plot of standardized residuals versus standardized predicted values. Okay. Okay. So once again, regardless of what you get, you're going to note it and then move on. Here we go. Last one, checking for normality of residuals. So there's a couple ways to do this. You can do this with a histogram. Okay. And we have our dependent variable of cholesterol concentration, our independent, and we have our regression standardized residual. What we're looking for here is it approximately normal? Does it kind of fit this normal curve? Probably yes. But what's even better is to use this normal PP plot that you produced. Okay, so here is what you're looking from the normal PP plot. If you are looking like this, you've got positive skewness. If you look like this, you have negative skewness. If you look like this, you have positive kurtosis. And if you look like this, you have negative kurtosis. Those are the 4 things you're primarily looking for. If you don't have any of those, you're pretty good to go. Okay. Now, they're saying that the diagram above shows that the data suffers slightly from positive kurtosis. However, even though it's good to assess normality. Normality is one of those things that tends to be kind of robust. It tends to not be as big a deal as some of the other assumptions. Okay. But in this case, the conclusion would be they're normally distributed at least enough. Okay. All right. And again, they recommend if you don't have normality, you might do a transformation, but we're going to press on regardless of whether or not we have normality. We're going to note it and press on. Okay. So finally, we get to interpret our results. Okay. So first, we're going to determine whether we have our model being a good fit to the data. And then we're going to understand the coefficients of the model, and then we can do some predictions. Now, the prediction part is what I showed you in the previous lecture with y hat equals ax bx plus a, excuse me, bx plus a. But they have a way you can actually do it with SPSS. I think it's more painful than actually just figuring it out, but there is a way to do it. All right. So determining how well the model fits. First of all, you can look at the percentage or proportion of variance explained using R-square and adjusted R-square. Now, our adjusted R-square is really the one you actually want to use because it's corrected. It's corrected for some potential bias. So we have 0.120. We are accounting for about 12% of the variance. Not bad. Not bad at all. And they just go through and explain that to you. Next, statistical significance of the model. Notice we have another ANOVA table, just like we had for ANOVA, except, as I pointed out, you have regression and residual as opposed to between and within. But you report it in very, very much the same way. You say F, this DF, 1,97 equals this number, 14.40, comma P, and this is giving you the non-APA version. The APA version would be P less than 0.001. P less than 0.001. Okay. All right. So now we can interpret the coefficients a little bit, and you saw this before as well. In fact, I'm going to scooch down a little bit to right here. So up here under B is your intercept. Down here is your slope. This is the one that we tend to pay most attention to. That's really critical. Notice the sig value, very nice, P less than 0.001. Just like it was above in the ANOVA, and that will always be the case. Those will always be the same. Okay. It also gives you a 95% confidence interval. Okay. So now we're kind of in business. Now we can use our formula down here, cholesterol concentration, our DV, equals our intercept, which is negative 0.944, right? Negative 0.944 plus 0.037 times whatever value we have for our time of TV. So if I'm interested in someone who spent 150 minutes watching TV per week, I'm not sure if this is per week or per day, but if they spend 150 minutes watching TV, I would plug in 150 right here into time TV, multiply it out, and then add the negative, or so, you know, take the negative minus, however you want to view that. I guess you can just say add the negative. That's probably slightly easier, 0.944. Okay. Okay. So you'll see how this looks in just a second. So they decided to look at 180 minutes. So they just put the 180 in here for time TV. And then we find out that the cholesterol concentration, the predicted cholesterol concentration is 5.72. 5.72. This is our expected value. This is the value on the line for the cholesterol concentration. This isn't saying what we got in our data, it's saying what we would predict in our population. Okay, so I would like you to understand and be able to apply that formula. However, I will also show you how you can do this using SPSS. Okay. All right, so the way you do it, you go under Analyze, you go under General Linear Model, you select Univariate. You're going to get this kind of setup for univariate. You put in your dependent variable under dependent and time TV under covariate. Now here's what's different, because I know we haven't really done this, but you're going to click paste. When you click paste, it opens up that third syntax window that we have not really dealt with. And here is what will appear in your syntax window. The next step is that you are going to, just before design equals time TV, you're going to create a new line right in here, right between criteria and design. And then you'll write in that line, L matrix equals all 160. Here it is. L matrix equals all 160. What does that mean? Okay. The all means that you're going to include both the intercept and the independent variable in your prediction. The numbers that follow, one tells it to use the intercept, and 160 is the value for X, the value for your independent variable that you want to get the dependent variable for. So then what they went ahead is that you can actually add multiple in here. L matrix, all 160, semicolon, all 170, all 180. That tells it that I would like to go ahead and get predictions when X is 160, when X is 170, when X is 180 minutes of TV time. Okay. After that, you have a choice here. You can either go to run all, maybe that's the easiest way to do it. So maybe I'll just leave it at that. Technically, you can highlight the whole thing and then press the little green triangle button, which is no longer showing, but I can show you. Yeah, here's your green triangle button. So you can just highlight the whole thing and press the green triangle button, or you can go under run all. Then you will get these results. Okay. 4.978 is your value of cholesterol when TV time is 160. Here's a confidence interval. 5.348 when your TV time is 170. Here's your confidence interval. And 5.718 when your try that one more time. 5.718 cholesterol. And here's your confidence interval when TV is 180. Okay. So then we get to reporting. How are we going to report this stuff out? And this is a fairly nice example. A linear regression was run to understand the effect of average daily time spent watching TV on cholesterol concentration. To assess linearity, a scatter plot of cholesterol concentration against average daily time spent watching TV with superimposed regression line was plotted. Visual inspection of these two plots indicated a linear relationship between the variables, There was homoscedasticity and normality of the residuals. One participant was an outlier with a cholesterol concentration of 7.98. I'm not sure how you read that, but 7.98. They were removed from the analysis due to not representing the target population. The predicted, sorry, I'm just making sure they covered all the assumptions here. They should have mentioned something about the, they did talk about the linearity, and they talked about the linear relationship and homoscedasticity and normality. They should have mentioned something about the Durbin-Watson as well, in my opinion. So you should mention something about the Durbin-Watson to talk about that. Okay. All right. The prediction equation was cholesterol concentration equals negative 0.94 plus 0.03697 times time. Average daily time spent watching TV statistically significantly predicted cholesterol concentration. Here's our ANOVA value, accounting for 12.9% of the variation in cholesterol concentration with an adjusted R squared of 12.0%, a medium effect size according to Cohen. You can leave out the medium effect size according to Cohen. There's some debate whether you should actually use an adjusted R squared for that purpose. So, well, no, I guess R squared is appropriate. Still, you can leave it out. You can leave that part out, okay? But notice how they do report the regular R squared and then the adjusted R squared, okay? An extra minute of daily average time spent watching TV leads to 0.037 with a 95% interval increase in cholesterol concentration. Predictions were made to determine mean cholesterol concentration for those people who watched a daily average of 160, 170, and 180 minutes of TV. 460 minutes, mean cholesterol concentration was predicted as 4.98, with a 95% confidence interval of 4.73 to 5.23. For 170 minutes, it was predicted as 5.35, 95% confidence interval 5.24 to 5.45, excuse me. And for 180 minutes, it was predicted as 5.72, 95% CI 5.53 to 5.90. Okay, so that's I gave you a couple of comments there. I would include the Durbin-Watson. I like how they did everything else, but you don't need to include the effect size piece, and that should do it. Okay, now a lovely graph or chart. How does that work with it? Okay. So you go into, if you want to show a chart that would go along with this, you'd go into Graphs Chart Builder. You'd go down to Scatter. You bring over the first one, just like so far, everything's the same, right? Bring over your time TV, your independent variable to X, and your cholesterol dependent variable to Y. Go ahead and set that Y-axis minimum to 0. Okay. And then you can click Apply. And then you can click OK. But here's the fun part. You'd like to add a line of best fit. So you activate the chart editor by double clicking on the scatter plot. So you've already gotten some output, right? You're going to double click inside that output, inside that graph. And then you're going to go under Elements, Fit Line at Total. Elements, Fit Line at Total. That will put in your regression line. like so. Okay. Now, under fit line, you want to make sure that it's linear, that's checked off. Okay, and that should be how it goes. But there's one more piece. They say there's two more pieces. I say there's one more piece. You can add a confidence interval and a prediction interval. Now, I think the prediction interval is a little bit nicer. So I'm just going to show you that. So I'm going to actually skip past this and show you that if you'd like to add a prediction interval, you just click off individual under confidence intervals. And then you'll get something like that. Okay, and that's just showing you for each value of X, what's the 95% confidence interval around the Y. Okay. And that's if you had done both kinds of intervals together. All right. So that is pretty much the linear regression. We can talk more about this in class and talk about homework and all that kind of good stuff. But that's all I have for you for today. So be well, take care. I'll talk to you next time.